and I'm here with Brian McLean and Nair Foster. And this presentation is about the component testing and calibration report. The components that we ended up testing were the pyroelectric infrared sensor, the ultrasonic sensor, the low power linear active thermistor, photoresistor, infrared optical tracking sensor, and the accelerometer. That also includes the gyro. So the first sensor that we're going to go over is a pyroelectric infrared sensor. The pyroelectric infrared sensor detects body heat and converts it into small voltage. There are two sensor elements inside of the lens, and these sensor elements are attached to a common power source, and a fluctuation in moving body heat will cause an imbalance in the circuit and trip the sensor. So to test the sensor, the ability to test the sensor was done at various distances to determine the maximum distance that the sensor would read the motion of a human. The viewing area was also to be tested. The sensor was connected to VCC, ground, and at the 4 input pin of the Arduino. The sensor would either read a 0 when no motion was detected, or a value of 1 when motion was detected. Both the maximum distance at no angle and the maximum distance at the maximum angle was tested. So the maximum distance with no angle was about 10 feet, 11 inches, and the maximum angle of detection was at an angle of about 40. So now we're testing the pyroelectric infrared sensor. Now, what this sensor is supposed to do is, once you move, the sensor is supposed to go from reading 0 to a 1, and as soon as it reads a 1, the LED will light up on the board. So I'm going to go ahead and move, and the sensor should read a 1, and it does. And once it did read a 1, the LED did light up like it should. The next sensor that we're going to talk about is the ultrasonic sensor. The ultrasonic sensor uses an ultrasonic wave to determine the distance of an object and how far it is away from the sensor itself. The sensor contains a sending and receiving sonar component to determine how far an object is from the sensor itself. The sonar signal is sent, bounces off an object, and the reflected sonar signal is then received by the sensor. With the proper algorithm, a microprocessor can be used to determine the distance the object is from the sensor. So when testing the component, theoretically, by having the time interval that it took the sonar to be received back to the sensor from the object, and multiplying the halved time by the speed of sound, the distance of the object could be computed. After the correct code has been inserted into the Arduino code composer and uploading the code to the Arduino Nano, the serial monitor displayed the proper distance of the object. Alright, so now we're testing the ultrasonic sensor. Now, what the sensor is supposed to do is it's supposed to tell the distance an object is from the actual sensor itself. So I'm going to put the object about a foot away from the actual sensor itself, and as you can see, the sensor is reading about a foot right now, and as I bring the object closer, the distance actually lowers as it should. And then when I extend the distance, the reading coincides and the distance is increased as I move the object further and further away. Depicted below is the chart along with the graph of the chart of the distance measured by the sensors versus the actual distance. The measured distance is fairly accurate to the actual distance. The distance was measured using a measuring tape, and the sensor was placed at every foot interval. The distance was displayed on the serial monitor provided by the Arduino application. The serial monitor displayed the distance measured by the sensor. At around the 9-foot mark, the distance deviated and the value jumped back and forth at a value of about 0.02 feet. The deviation became worse the further back the obstacle was from the sensor itself. So a conclusion can be made that to read a distance that is constant and consistent, a distance that is less than 9 feet is required to achieve such accuracy. The next sensor we're going to talk about is the low power linear active thermistor. And the thermistor is a sensor which has the properties of a resistor. The value of the resistance on a thermistor is dependent on the ambient temperature. When incorporated with another resistor and connected to power, the thermistor, because of its various states of resistances depending on the temperature, will output a voltage proportional to the other resistance in the circuit. In other words, the circuit which incorporates a thermistor and a resistor will behave as a voltage divider. The divided voltage will serve as the variable to determine the temperature that the thermistor is reading. To test the thermistor, a 5-volt source was connected to one end of the thermistor and the other end of the thermistor was connected to a resistor that was connected to ground on the other end. A probe was placed between the thermistor and resistor, and the probe served as the input into the Arduino.
Now we're testing the temperature sensor. On the screen, we've taken the raw values from the sensor and converted it to Celsius. So that's the current room temperature. If I touch the sensor, and it will start to warm up. It's at 32 degrees now, 33, and if I let go, it will slowly return to the room temperature. The infrared optical tracking sensor, the TCR T5000, it consists of an infrared light diode and a phototransistor that will reject natural light and receive infrared light. The peak operating distance is about 2.5 millimeters, and the output current is 1 milliamp, and it has a total power consumption of about 200 milliwatts. For the testing, 260 ohm resistor was placed at R1. A 10 kilo ohm resistor was placed at R2. It's in the schematic that we have on the previous slide. And the output of the schematic was placed and coded as an input of the pin A1. Now we're testing the infrared optical tracking sensor. This sensor sends out light pulses, and it waits and it reads the reflection on the other diode. Right now it's pointed up to the ceiling. It's reading roughly a little over 870 raw value. If I put my hand above it, you can see my hand starts to make it starts picking up my hand around this height. And the closer I move in, the lower the value will get. If I'm on top of it, the min is about 35, 30 to 38. And if I remove my hand, it goes back to the max.
The next is going to be the photoresistor, the GL55 series. The photoresistor is a resistor made up of semiconductor material. As the lumens change in a room, so does the property of the conductance. Depending on the amount of lumens that the sensor is exposed to, the resistance of the photoresistor will increase or decrease. The more resistance the sensor detects, the greater the resistance. The peak value of the photoresistor is about 540. The light resistance varies from 5 to 2,000 kiloohms. The dark resistance varies from 0.5 to 10 megaohms. The typical increased lumens response time is 20 milliseconds. The typical decrease lumens response time is 30 milliseconds. The maximum voltage and power are 150 volts and 90 watts. Here's a video that's going to show how we tested the photoresistor. It was connected to an LED. One leg of the photoresistor was placed on the ground, and then the other leg was placed in between a 10 kiloohm resistor, and then the output was taken from the intersection of the leg of the photoresistor and the resistor. And then we had another pin going to the LED, which turned the light on if the resistance from the photoresistor rose above 400.
We're testing the GL55 photoresistor light sensor. The sensor is already calibrated for this room. If the raw value from the sensor goes above 700, the LED will turn on. Right now it's reading 380 approximately on average. If I put my finger over the sensor, the value will increase. It's at 600 now. The closer I get, and once it's over 700, the LED will turn on and stay on.
The next sensor is going to be the axis accelerometer and gyro. Its model is the GY521. We took this device, the 3-axis gyro accelerometer. It has a 16-bit analog to digital converter. With that, it's able to capture the X, Y, and Z coordinates. On different Arduino microcontrollers, there is an I2C bus interface. With this, with the sense, with the microcontroller that we have, the Nano, you would have to use A4 and A5 to connect the pins to the pins SCL and SDA. The accelerometer can simulate up to 16 Gs. The sensor also contains motion detecting capabilities. With the sensor lying flat and facing up, the y-axis is positioned on the north end of the sensor. Positive x-axis is on the right side, and the positive z-axis is on the top of the sensor, as pictured. The 4 ports on the sensor that we'll be using is the VCC, ground, SDA, and SCL, which are both those are connected to A4 and A5 on the Nano.
Now we're testing the gyro sensor. The outputs on the screen are going to be the accelerometer, the Y, X, and Z axis. It also gives a temperature, and it also gives the gyro sensor X, Y, and Z axis. Now, for the temperature, if I put my finger on the device, you can see the temperatures. It went up by a degree, and if I rub it, it should go up even more. And now for the gyro sensor, if I start moving the board, the values will start to change, which they did. And it will change according to how the board's orientated. So different orientation will give you different values, as well as for the gyro sensor.
And here are some of the references that we used to create this PowerPoint and the data sheets for some of the for all of the sensors.